Okay, last question on this handout from that lab session, where all the questions, except for the first one, are from Chapter 16. Great questions. So in this one it says sorbic acid is used as a food preservative. Go check out those labels and you'll see this name. Or more likely, you'll see potassium sorbate, because it goes on to say this potassium salt of the conjugate base, so potassium sorbate, is added to cheese, for example, to inhibit the formation of mold. What is the pH of a 0.37 molar potassium sorbate aqueous solution? So first things first, sorbic acid. A lot of the organic, if not all of the organic acids, are known by what are called these common names and not the IUPAC formal nomenclature. And they give us the structure. It's got a conjugated hydrocarbon end, doesn't it? With alternating single and double bonds. It ends in a functional group, COOH. Okay. So 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5 carbons, and then a COOH. So specifically it is CH3 on the end. And then this carbon has 1, 2, 3, or 2, 4, 6. So it needs another bond. So it's got one hydrogen. CH. So it's CH3, CH, 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 CH. 4 times. That brings us to here. And then this carbon we write as C and continue OOH. All right? So there it is. That's my sorbic acid. And that's the acid. What would be the conjugate base? Well, I would remove that proton. And so my conjugate base of sorbic acid would be sorbate. That's my conjugate base. And we see it is an anion. So potassium sorbate, even though we write the cation first and then the anion, I want to put the two of them together, close together. So I'll write potassium sorbate, sort of as sorbate potassium. Okay, and that's my salt. Specifically, it's my sodium salt of the conjugate base of sorbic acid. So we see all the relationship. Now we have in this question a 0.37 molar solution of potassium sorbate in water. So what happens when we put this guy in water? Well, let's do it and find out. CH3, CH 4 times, COO minus, Na plus. All sodium salts, you know them as completely soluble. So when I put this into water, quite literally adding it to water, this is a strong electrolyte. So I actually get stoichiometric amount of my sodium ion and my sorbate anion. Okay, you would have predicted that. 1 to 1 to 1. So there's no K here because this is stoichiometric, it's 100%, it's just a salt like sodium chloride dissolving in water. But the thing of it is that one of these ions, specifically the sorbate ion, because it is a conjugate base of a weak acid, then when this goes into water, it might change the pH to basic. So that's what this question is really asking. Okay, what is the pH of the solution when it's 0.37 molar potassium sorbate. Well, 0.37 molar potassium sorbate is actually 0.37 molar because it produces a stoichiometric amount, right? It's 0.37 molar sorbate. And so now we can write our equilibrium. CH3, CH4, COO minus, aqueous. Let's put that in water because that's the major species. That's what's really going on in the sodium. So there's none of this left. And the sodium is spectator. It's not acidic or basic. This guy is basic. So let's get the whole picture by putting this according to KB, right? Because that's a base, into water, and it's going to form the conjugate acid, sorbic acid. I'm just going to write sorbic acid as SA because I'm running out of room, plus OH minus. Okay, so this initially is 0.37 molar. Water we don't care about. Initially none of this. Minus X plus X plus X. So at equilibrium, 0.37 minus X, X, and X. Do we have a K? We have a pKa, but we need a Kb. So Kb is equal to X squared over 0.37 minus X. We want to know what the pH is, so we really want to find out X, and then X will be the concentration of OH minus, then we can get a POH, and then from that we can get a pH. But we have to fill in the value for Kb. And we don't have the Kb exactly, we only know the Ka. In fact, we know the pKa. We know that the pKa value is 4.77 for sorbic acid. Therefore, the pKb would be that number from 14. So that's 9.23. And therefore, my Kb is 10 to the minus 9.23. And that comes out to be 5.89 times 10 to the minus 10. Great. So back to here, then 5.89 times 10 to the minus 10, that's a really small number, is equal to X squared over 0.37 minus X. Well, look, Kb is so small that X is going to be tiny, right? The smaller the K, the smaller the change. So that change very definitely is insignificant compared to the 0.37. So we'll say about equal to, and we'll use our little 5% rule there. Okay? And so therefore X squared is equal to 5.89 times 10 to the minus 10 times 0.37. Solve for X. We get X being equal to 1.4 times 10 to the minus 5 molar. Now what was X? X is my OH minus concentration at equilibrium. Therefore, my POH is the negative log of this number, and that's 4.83. And finally, my pH is equal to 14 minus 4.83, and that's 9.17. And that makes sense. I was expecting a basic pH because this was a solution of the base. It was a solution of the conjugate base of sorbic acid in water. So there's your final answer, 9.17. And that's the final question also on this handout from mainly chapter 16. So great stuff, great review for the exam.